Dear all, today we have a special guest. Now I call upon Tangaramya ma'am, CSD HOD, to introduce the chief guest.
Sir, good morning, sir. Won Yoon, sir. Hope you remember us. Welcome to RMK in virtual mode. It's my pleasure in introducing the guest of the day. Won Yoon, sir. He's a professor and he's a recipient of the Sunny Chancellor's Award for Excellence in Scholarship and Creative Activities in 2019, and highly successful researcher who leads many productive long-term industry collaborations. Professor Yoon received his doctoral degree in School of Industrial Engineering at Purdue University, and he joined the faculty of the Western Watson School in the Department of System Science and Industrial Engineering at State University of New York in Binghamton in 2010. Professor Yoon is currently a professor in addition. He has a joint title in School of Commerce at Waseda University, Tokyo, Japan, and is also visiting professor in Nirma University, Ahmedabad, India. Professor Yoon directs the Complex System Design and Analysis Laboratory as a faculty member of the Western University for Systems Excellence. He leads collaborations with faculty, staff, students, and industry partners such as Analog Devices, Samsung, Sanmia, SEI, and it's my pleasure in welcome you for the today's session. Over to you, sir. Thank you.
Okay, I hope you guys can hear me. Let me put the slideshow mode. Do you see my slide okay?
Yes, sir, it's visible.
Okay. So I'm gonna present this one in the slideshow mode. So I may not be able to check out the chat window. So in case you have any question during my presentation, please type in your question in the chat box, and I'll try to address all the questions after my presentation. Okay.
Sure, sir. You're loud and clear, sir. Thank you, sir.
Okay, so the title of this talk is slightly different from the the brochure that you guys must have. So this is a digital transformation using AI machine learning in the electronics manufacturing. So we have done a lot of the smart manufacturing concept in the electronics manufacturing. So under the Industry 4.0 concept, I would like to highlight the electronics manufacturing as one of the Industry 4.0 application. Okay. So this is a slide that I like to use it as an intro of my talk. So what will be the driving force of the Industry 4.0? So a lot of people talk about the Industry 4.0 many different ways. So I would like you to actually focus on this figure first. Let me change the pointer. So in this figure, so we do have Industry 4.0. So there are many discussion about the Industry 4.0, how to define the Industry 4.0. But nobody will argue that the Industry 4.0 will be the combination of the many different technology that the mankind has developed, the many decades. Okay, so robotic, Internet of Things, and Internet of Things in simple term, it's gonna be sensors and different type of sensors, simulation, big data, cloud computing, system integration, cybersecurity, and et cetera, et cetera. So there are many things that out there. Maybe like this is not everything about the every technology and every method that we are going to use under the Industry 4.0 concept. So, but this is just some example. So we have to integrate so many different technology and so many different data method and whatnot. So how we can actually integrate everything together and make the one voice so that we can control the factory or the warehouse without human being there. So AI, machine learning algorithm, AI method, maybe the backbone of the Industry 4.0. So all this technology, if you look at the individual technology, robotic and Internet of Things, and then simulation and system integration, and all these things, individual item has been developed many decades. But Industry 4.0 concept requires the consolidating everything. So AI may be the one that who can help us. And then if you look at this chart, so AI and the machine learning is not new. AI concept was introduced in the 1950s, and the machine learning algorithm introduced in the 1980s. The question is, AI was there, robotics was there, and then all the sensors and big data was there. But while we are talking about the Industry 4.0 now, maybe past a decade. So if you look at this chart, so this can answer those questions. So for example, cost of the data handling compared to the 2004 and 2014 is 98% cheaper, as an example. And if you look at the 2022, probably compared to the 2004, maybe to 99 or more than 99% cheaper. And if you look at the cost of the bandwidth, and this is the telecommunication channels and whatnot, so it's 80% cheaper compared to the 2015 and 2020. But if you look at the 2022, maybe it's even cheaper than that. Cost of hardware in 5 years, it's only the half price. So mobile devices has been increasing. Adaptation of the mobile device has been increasing. So all these hardware changes and all those things, perhaps that make us realize that maybe it's time that we can realize the Industry 4.0 with help of the AI machine learning algorithm. So that's kind of the area that I believe that we're living. Okay. Under that, so I'm not sure how many people understand the smart electronics manufacturing. So if you look at the Nissan news, and US will be bringing a lot of the semiconductor industry back to US. And then the electronics manufacturing that I'm about to talk about is not the front end of the semiconductor. So which is, I think I'm going to talk about the PCB assembly line, which is a back end of the semiconductor process. As an example, so wafer manufacturing or the die design will be the starting of the semiconductor business. After the die is built, and we have to package it with the different wires, bonding and whatnot. And after that, we have to put those chips over the PCB board, and then those PCB board goes to the consumer product like Apple Watch, iPhone, Galaxy, and whatever. So what I'm about to talk about in today's talk is talking about how to apply the Industry 4.0 concept mainly in the PCB assembly line. But I believe that this kind of the concept can be applied to the many different industries. So I hope that you can project this kind of concept and technology can be applied to the many different manufacturing with the Industry 4.0 concept. So under that, I will introduce the smart electronics manufacturing concept and AI-based closed-loop control. And after that, I have 3 main topics that I'm gonna talk about. So one is online, offline control of the stencil printing process and how to apply the AI machine learning algorithm. Second topic is a mounter, how to select the optimal position of the component, because a mounter has some sort of the deviation from the center, how to pick up the good location and then make sure that the components stay in the center of the pad. And then finally, there's a reflow, how to optimize the reflow. So in short, in terms of the PCB assembly line is consisting of the 3 elements, which is a stencil printing, mounting, and reflow. So I'm talk about all those things, and after that, I'll talk about the future of this kind of the PCB assembly line or the smart electronics manufacturing factory. So that will be the conclusion of today's talk. So this is a concept of the smart electronics manufacturing. So we like to make a manufacturing system much more intelligent. So in our campus, I'm coming from the State University of New York at Binghamton. So we do have a smart electronics manufacturing lab. And smart electronics manufacturing lab consists of all this kind of the equipments. I believe they're combining all this equipment together. I think we're looking at around 1.5 to the $2 million worth of the equipments. So we do have a functional PCB assembly line. So let me talk about this one. Around 2016, we established this lab. So there's a 2 stencil printer, one from Accra in German, and another machine, NPM, from the Boston, US. And then we have 2 printer. And then we have a SPI machine, which is inspection machine. And then we have 2 types of the mounter. One is universal, and the other one is a Fuji high-speed mounter. And then another inspection machine, it's called automated optical inspection machine. And then Reflow oven, and another post automated optical inspection machine. So this is a typical PCB assembly line. Only difference is probably the printer, most of the time they are using only one, and mounter, depending on the number of components they have to place on the PC board, and many times like you will see a series of the mounters, chip mounters, okay? So that's kind of the other line that you're seeing it. So our students are printing and then testing, and also create the smart electronics manufacturing solution. As an example, let me briefly explain it. So we have actually the printer side of the study, and then mounter side of the study. And since 2022, and then we've been studying the reflow. At the moment, and we are trying to combine the different data together and optimize the different part of the PCB assembly line. In short, I have a next slide, and I can explain this one a little better. So we are developing the closed-loop feedback control system. So as an example, so the stencil printer will print it, and then this one will go to the SPI machine, and SPI machine will inspect the quality of the stencil printing. So in Industry 4.0 concept, who's the controller? Who should be the controller? That's the question that you can ask. The SPI machine is inspection machine. So we will know what are the setting of the stencil printer, and then the result of the stencil printer. So the inspection machine perhaps will contain the most of the data. And then we do have a 3 inspection machine in this line, SPI, and then 2 AUI machines and whatnot. Okay, so using this inspection machine, can we have a closed-loop feedback control system? So printed, PC board is coming to the SPI machine, and then we gather the data, and using this data, we control the machine and new parameters. In terms of the mounter, we have SPI and AUI information, and then gather the data and control the mounter setting. And then reflow, once we have a pre and AUI information, and based on this information, can we optimize the reflow setting? So those are kind of the concept, and I'll have a more detailed slide, and I'll talk about it. By doing that, we can improve the yield and minimize the defect, and we can also have a real-time control system, okay? And then I'll walk you through what type of research that we have done in this domain. So before that, so this is a kind of the eye chart of our lab, what kind of the PC board, and then what kind of the soda paste, and what kind of the plate, and what kind of the components that we are using here. So this is a kind of the summary. So we do have many different testing vehicles. And then we tested more than actually the 10,000 PC board as of now. So if you look at the stencil printing, so this is another eye chart. So there's a stencil, okay, and then there's a soda paste, and then printer setup, and then printing machine. So printing setup and the printing machine is a soda paste, or the stencil printing is what I'm talking about. And then there's an environmental factor. So for example, humidity, and then temperature, and airflow, and then human factor. Those are the things that we may not be able to control, okay, as an example, because it's keep on changing it. And then stencil, before you go to the manufacturing, and usually the type of a stencil, or the coating, laser coating, or the nano coating, and then different type of stencil, all those things are decided already. So during the production, or during the manufacturing, we're not gonna make changes on the stencil. If there's a worn out stencil, we may replace it, but we're not gonna change the characteristic of the stencil. In terms of soda paste, it's the same thing. Soda paste is also the important part of the puzzle, but the viscosity and then particle size and on that. So soda paste is decided. And once they manufacturing system decide to use the different type of the soda paste, they stay with it, okay? And then machine, you cannot easily replace the machine. So if you look at the entire stencil printing factors, and printer setup is the only thing that we can control as a part of the intelligent manufacturing, okay? So there's a squeeze pressure, speed, and printing direction, and snap of distance and separation speed. So as an example, and snap of distance is based on the multiple, so many iteration and of the experiments, we know what is the required step of distance. So and then it doesn't vary much depending on the different stencil and soda paste, and we know that. So if you look at the this one, and squeeze pressure and speed will be the most critical. Printing direction is sometimes you can print it as a forward and backward. Depending on the different direction, you may have a different optimal setting. So technically, we control 3 settings: squeeze pressure and speed and separation speed. So those are the 3 things that we control, and depending on the different printing direction, and we have to optimize it, okay? And then also in terms of the PCB assembly line, about the 70% of the PCB assembly defect and errors are coming from the printing. So the printing is one of the important steps. So let me explain the AI machine learning based the crossover feedback control system one more time. So we are going to apply the AI machine learning algorithm. So we are developing an AI machine learning algorithm, and the AI machine learning algorithm will be embedded in the inspection machine. So here, and here, okay? And then once the result is coming into the this machine, data is PC board is coming to this one, and then we inspect it, and the inspection result goes to the AI machine learning engine, and then we provide the better setting as needed, okay? Because this is a production line and we're looking at the CPK, CPKM, offset, and defect, and all those things are factors, all the metrics, okay? So based on the real-time control, and then we want to do it. So in here, so let me explain this one, the 3 things. The PAM is our concept of the offline control. So for example, before you go to the manufacturing and you want to identify the what is the optimal setting, so this PAM will give us the offline optimal solution. And then POM is online optimizer. So before you start the manufacturing system, and based on some DOE and sample data collection, and we can optimize the setting. That's a PAM. And then POM is once we start doing the manufacturing, we can collect the real-time data and then make some adjustment. So that's the online, okay? PDM is the diagnostic module. So which means we don't want to have not so good data coming into the AI machine learning engine. So this one, PDM, is checking out the abnormal behavior of the system, or the data is the abnormal. Then we don't want to add this one to the AI machine learning engine. Instead, we can actually filter them out, or we can detect the root cause of the problem and then do that. Okay, so I spend a little bit more time on the printer side because the other side is the same thing. So mounter, we are going to have a offline control and online control and diagnostic module, but offline control is more like a calibration of the machine, because this chip mounted machine will pick up the component and move the component and place them on the PCB board, printed circuit board, okay? So that's a calibration is offline control. And then we are interested in online control, and then MDM, which is a diagnostic module. So Reflow, I have a separate slide, and I'll explain this one in the later slide, okay? So I think this is, I spend a little more time and I explain this one, but the other slide, I can go a little bit quickly. So online, offline, and diagnostic module. So you can see offline control, online control, and diagnostic module. And you collect the data from the printer, and then SPI machine will give us a feedback control and collect the data feedback control, okay? So what we are trying to do is based on that. Let's say when you collect the data out of the inspection machines, and you see a lot of deviation of the outcome, and then we want to have a shorter deviation. And also that there's a target volume of the stencil printing result. Let's say this is 100% is a target, and typically industry allowed to accept, plus minus like 30% or the plus minus 50%. As an example, 70 to 130. If you want to have a little bit tighter control, then 70 and then 130% of the printing volume will be accepted. And if you relax, and 50 to 150 will be collected. So if you want to have a tighter control, and then you probably will need to have this kind of the controlling system. Another way that you can do is you can have a real expert of the sort of printing engineer and stay next to the line. But if you're looking at the Foxconn, Samsung, like a Bosch, I mean, all the big company, they have maybe hundreds of this kind of line, and you cannot have those engineers stay in next to the every line. So that's why we want to create this kind of smart system, smart intelligent AI machine learning based system, so that we can mimic what expert can do without having them on in the line. Okay, by doing that, we can achieve so many different benefits. Reliability will increase, consistency, and that will minimize the defect, and then improve the yield and then efficiency. Okay. So we actually have, we developed the AI machine learning algorithm, and then I'm just showing you the results. So let's say there is a PCB board, okay? So we've been partnering with some company, and then they actually brought us the automotive PCB board. And this is the engineer suggested. So you need to use the squeeze pressure as a 7.2, and speed is 50.8, and 1.3 as a separation speed. So those are the kind of the speed the Unity have. So this is their known optimal solution. Without teaching, without providing this information to the AI machine learning algorithm, and then our PEM come up with this solution, 6.0, 60.5, and then 5. So those kind of the result that we got. And then based on, and then we actually tested in the same line, same PCB assembly line, and with this setting, okay, customers best known, and then our AI machine learning algorithm solution, and it turns out then CPK is improving about 56%. And then this is another test. So we see significant improvement from the customer best known, and then AI-based solution. Another thing that I like to highlight is speed. So if you compare the customer's best known solution and versus this one, this is a little higher pressure and a little less speed. But if you look at this one, AI is suggesting a little bit faster speed. So that means technically with the same amount of time, and then you can produce the more PCB board, because the speed is slightly higher, maybe like 10%, 20% faster. Okay, so that's kind of another benefit that we are going to get it out of it. Okay, and this is the actual testing result. So this is another eye chart. So let me show you this one. So this orange line is indicating before this one is a PEM, and after this one is the POM. So we collect the DOE data, design of the experimental data, and then optimize it. So this is what's happening. So CPK will be improving based on the number of data that you're collecting. After that, online data comes in. So when you're receiving the more data, it's not always guaranteed that your result is going up. So sometimes CPK coming down and coming up and whatnot, but ultimately we like to achieve the higher CPK. Okay, so in order to test it, this kind of environment, we cannot always do the printing. So we actually developed the bit of the digital twin concept. So how can we develop the stencil printing in the virtual environment so that we can actually do so many different iterations and come up with the solution? So in this case, we kind of divide the signal as a two piece. One is the true signal, and the other one is the noisy signal. And by combining them together, and we always keep on changing the noisy signal. So whenever we got the different solution, and we can test it. So this is kind of the one method. And another thing is if you look at this one, so maybe like a CPK improvement is you can sometimes drop it and sometimes it's going up. But the question is, how often do you want to make changes on the mechanical setting, like a printing speed and then pressures and whatnot. So it's not easy to make changes like every iteration. So we are going to check it. So maybe like a printing setting doesn't change it much between this and that, as an example. Then even though we maybe improve the CPK slightly, and we don't want to make changes. But if we see the true optimal signal, while we are going through this kind of process, and then we are going to make changes. Again, this is the kind of the monitoring, and then we're not going to make changes. We're not going to make changes. But once we see the significant improvement from the one CPK to the other CPK, and then we are making changes, as an example. So this is kind of the illustration of the real-time optimization. Okay. So diagnosis, stencil printing diagnosis. So we have done a few things. So abnormality detection and cleaning frequency and then cleaning profile. So as an example, because we're using stencil have a soda paste above, and then it will squeeze, and then soda paste will come out in the through hole and place on the PCB. And because there's also snap up, and then there's a little bit of short distance between the PCB and then the stencil. And bottom of the stencil, it will create some residuals, soda paste residuals every once in a while, and then you have to clean it. This is one of the big issue. So how open you want to clean bottom of the stencil? What type of the cleaning profile do you want to have it? Sometimes you have to clean it with the dry. Sometimes you have to clean it with a wet. So as an example, let's say you are cleaning up your house, and you can just mop it and then broom it with a dry method. It's gonna make your room clean. But if you want to make it super clean, maybe you can use the water, okay, to clean up your room, and then your room will be much cleaner. So there's a different type of cleaning, dry and wet, and this is frequency. And then also, if there's any kind of the abnormality behavior, we like to detect it. So this is kind of the 3 modules that we have. So as an example, we got the sample data, and then we apply the deep learning method. And then this is sort of the PCB board, and you can see it. So we know there's a lot of sort of low soda paste and then braid defects. And then there are 9 different kind of the root causes. And if you apply the exception network method, and then we're able to identify the 82% accuracy, percent of the accuracy, saying that this is one of this kind of error. But if you have 6 classes, and then we can identify about 86.79% of the defects. Because we do not have a lot of data when we apply this one. But imagine when we are applying this one in the actual manufacturing line, and we're gonna collect the more data. I believe the exception network or any deep learning method will perform better. Okay. So this is what I mentioned to you about the cleaning. So let's say look at the stencil, and bottom of the stencil, you can see a lot of the clogs and residual building up at the bottom of the stencil. Actually, this is the photo taken by the students. So here's another picture. So you have a stencil, you have PC board, and then through all technology, we're putting this one. And after that, we snap up, and then the stencil will be lifted up from the PC board. Then you can see like there's some kind of residual and sticking in. And then we have to clean up this one every once in a while. So the main idea that we have here is, so we actually took up the older photos, and then as you can see here, but in order to take a photo, if you take a photo and then detect it, oh, there's a residual, let's clean it. So the question becomes, how long does it take to take a photo? For example, if you printed one PCB board, you may take maybe like a 14-second or 15-second or something like that, less than 20 seconds as an example. But if you take a photo with a high resolution and process the image file and then doing something, it will take a couple minutes. So that means if you take a photo of the bottom of the stencil and provide some kind of the solution, and it will not work, as an example, Okay, so our idea is, why don't we estimate the amount of the residuals building up? So we build the algorithm, long-term, short-term memory-based algorithm, and we estimate the amount of the residuals building up. And then based on that, and we can decide it, what kind of the cleaning frequency and then cleaning cycle that we have to do. So that's kind of the study that we have done it, okay? And here's another thing. So if you look at the assembly line, so think about it, one PC board goes to the printer, and then this PC board will go to the inspection machine, while one machine is going to the next machine, and then the previous machine, the printer will receive the next PC board. So which means if you predict what kind of the setting that you have to change it in one board after, it will not work, as an example. So if you print it, if you receive the data and then predict it, you have to predict it 2 board after. So meaning you're not predicting, let's say you're making a line. So as an example, let's say you're making a line. So it's one guy is being served, and then there is another guy is also being served. So by the time you receive the data and then identify the another optimal setting, you cannot apply this one because it's too late. So you have to apply this one is another guy, one guy after. So this is a kind of the illustration. So using 2 data, and this is the first one and second one, and you have to predict the behavior of the first one, because the third one is already too late, because this one is in the stencil printer, and then it's already printed. Using 3 data, we have to predict it, 5th one. And same thing, using 5 data, we have to predict it, 6th one, as an example. So this is kind of the study that we have done, and you can see the result here, okay? And then the bottom of the stencil, once we understand the bottom of stencil, and then another thing is a dry cleaning profile and a wet cleaning profile. So there are different features here. So volume averages, standard deviation, and defect warning and whatnot. So this is all the numerical data. But we like to use the some deep learning method. So student developed the based on this numerical data, we developed some kind of the image file. So this image file is illustrating certain type of volume, certain type of standard deviation and defects and whatnot. And we actually developed the stacking images with the RBG. And then based on this RBG file, and then she applied the some deep learning method, and then identify the do we need to use the dry cleaning and wet cleaning. So you may consider wet cleaning will clean up the bottom of the stencil much cleaner than the dry cleaning. Then you may actually question, okay, then why don't we actually use the wet cleaning all the time? Because of the timing. So manufacturing, the throughput is the most important thing. So dry cleaning doesn't require the a lot of time. Let's say dry cleaning takes, let's say 30 seconds, but wet cleaning could take 2 minutes because you're using solvents, some alcohol, and then clean up. So you need to dry up those the solvent alcohol, so that those alcohol and solvent will not affect the soda joint, soda paste in the next iteration. So it takes longer time. So if you use the more wet cleaning, and you will delay, okay? And then cleaning itself is the delaying the throughput, but out of the dry and the wet cleaning, and wet cleaning delay the process much longer, as an example. So we want to minimize the wet cleaning, and we want to minimize the dry cleaning as much as possible. So we developed the optimal cleaning profile selection and optimal cleaning cycle selection model, and then combining cleaning cycle and then profile together. Okay, so this is a kind of example. So we got the board from some company, and then applying our cleaning profile solution, and then we are able to improve the CPK around 13%. Okay, so moving on to the mounter. Give me 1 second. Looks like there's some chat box. Okay. Okay, so I don't think we have much time. So let me quickly explain this one. So the mounter study, same thing. So I explained this one before. So we have an online setting, and then the diagnostic module. So in short, maybe I can explain that this one, the entire concept of this one with this slide. So there is a pad and there is the soda paste, and these two things are usually misaligned. Okay, and so many reasons. And after that, you have to put the component. So if you look at the Fuji, Panasonic, like Universal, like the major chip mounted company, the default setting is to place the component on the center of the pad. Because the pad location is given from the job file, so you can easily place the components over that, okay? And then the Panasonic have a pattern, which is the APC module. So what they're doing is instead of putting the component on the center of the pad, and they like to put the component on the center of the paste, sort of paste. So that's kind of it's a pattern. So you can Google it and then Panasonic APC, and then you can find their solution. But our idea is it may not be the center of the pad, it may not be center of the paste, it may be in between. But we don't know exact location, so this is what we are trying to find out. Okay, and then after that, we like to have this kind of the result. So this is showing the results. So let's highlight it. So blue is the placement location that we design it, and then red is the default setting, and then the green is the Panasonic result. So if you place the component in between, somewhere else, then finally after the reflow, and then components come to the center. So this black dot is coming to the center. So we can see this one from our experiments. And then there's also the software who can actually do the similar work, which is called the surface eval. But we learned that the physical model or the numerical model not always providing the result from the actual experiments. So our data-driven model and then the surface eval model and then doesn't give us the same answer. So our idea is perhaps that we have to use the data-driven model to train the physical model or the numerical model, or maybe like compensate some of the physical or the numerical model. So that was our concept. So let me just skip this one. And then, so the machine learning based online cross replacement control works like the same thing. So we have SPI data, and then we use the dynamic placements options and machine learning algorithm and decision-making module, and then generate the alpha file so that the placement machine will listen to this alpha file and place it, meaning it's not going to place the center and slightly off, as an example. So that's kind of the concept of this one. By doing that, so this MOM is online, the amount of control will minimize the deviation like around 30% compared to the default, which means place the component on the center of the pad. Okay, that's an example. So I'm gonna skip this one. So in terms of the diagnostic module, so same concept compared to the printer. So we want to use the different diagnostic module. And here's example. So what about the nozzle size is a different incorrect nozzle size? How can we optimize it? What about the pickup position is different from the center, and how we can do it? And then the nozzle contamination. What if there's a contamination on the nozzle, and how can you deal with it? Okay. So based on the multi-criteria output, like a classification module, and then we achieve the overall accuracy of about the 85%. But if you want to detect it like a single category classification model, like a nozzle size is 92, pickup position is 100%, and then contamination is 97%. So we also developed this module. So moving on, so this is I will probably spend another 2-3 minutes, and after that, if we have time, I'll spend another few minutes, and then I'll take some questions. So the recipe optimization. So this is the reflow oven. So if you look at the reflow oven, then there are different time zones. So this one is 100 Celsius, 140 Celsius, 155, and 270, something like that. Let's say this is a 6 zone. So the control parameter is a discrete parameter. So this is temperature 1, 2, 3, 4, 5, 6. So we have 6 different temperature. PC board is coming into the board and then flow down entire process, and then it will generate the joint. So our control parameters are deterministic, but at output of the temperature on the PC board, we'll have to follow this kind of the nonlinear line. So what kind of the temperature setting we have to have so that it's not the board temperature, the joint temperature. Sometimes if you look at the BGA QFP, the joint is under the component. Some of the BGA is very big. So the joint temperature has to follow the exact line. So how can we do that? Okay, so that's kind of our research question. And this is a kind of our oven, and then this is the kind of thermocouples, and then we do that. So our idea is this one. So we need to collect the data, but we want to minimize the number of data collection. So initial data collection is based on the heat transfer equation, like a simple heat transfer equation, and we collect we have some kind of the setting, and we collect the data, the one board. Typically, if you go to industry and then they collect a lot of data by you doing this kind of the thermocouples. Okay, but we collect the one board. And out of the one board, and we develop the prediction model, and then we optimize the prediction model. Okay, so out of the one board, and then we develop the prediction model and then optimize it. So this is kind of the process that we're seeing it. And we can see that we can develop the prediction model almost like a 95% accuracy. R-scale value is 0.95, which is very high. Okay. And after that, after we have a prediction model, after that we are developing the what kind of the temperature setting that we have to have it. So depending on the different reflow oven, sometimes you have 6 zone and sometimes 7. I was told that you can have a 12 different temperature zone. So we can actually optimize it based on that. Okay. And then here's the result. So this is a target, and then this is a predicted. So target as we have engineers, and engineers believe that this should be the temperature that we have to use it for our test vehicle. And then the predicted one is this one. So which means it's a slightly higher in some of the places, especially the zone 6 is a higher. And after that there's a cooling. So and then the average gap is less than, plus minus, 2 or 5 or something like that. So that's kind of the gap. So the AI machine learning based algorithm will use only the one data points, one like PC board, the thermocouple flow, and then we collect the data, and based on that we can optimize it. Okay. And then we identify compared to these two, and then the AI based predicted and the result is actually performing better. And then this is something that we discovered recently and compared to this one, because a higher temperature will increase the time above the liquidus, meaning make it so that joints are more liquid type. So which will create the better joint, which will create the better self-alignment. So we learned that the predicted module works better than the human decision. So in terms of the future integration, so again, we've been working on the printer and an SPI machine, and then mounter and an AUI machine, and then reflow to the post AUI machine. So this is kind of the single machine or the maybe 2 inspection machine, like a cross feedback control system. So in the end, we like to actually put it this one. And then right now, there are some kind of the set-top box computer, like a GPU machine computer inside this inspection machine and does all the control. But in the end, I would like to put everything in the high performance computing in the cloud system. And this is a one line, but if you look at the multiple line, it can be hundreds of the line. Then we can control all this system, the factory level system from the cloud-based intelligence platform. And this is what we are heading to. So let me explain our current research. As the last topic, our current research is from here, from the inspection result here, and we like to predict at the end of the line what will be the outcome of this one. Okay, and then same thing based on these two, and then we like to predict what will be the outcome of the end. So that's what we are interested in. Okay. So if we are completing this one, I think we should be improve the smart manufacturing concept, like maybe 2 steps better than where we are now. Okay, and also a lot of things that I'm proposing today has been implemented with the sponsor company, and our solutions are sort of embedded in the line, and then a lot of the companies are using the solution that I am presenting today. Okay, so thank you very much, and I'd like to highlight the Dr. Won. So Dr. Won and myself are actually working on this project together. Currently, we have 4 students working on this project, and so far we actually published maybe like more than 20 papers out of this topic in the conference and journals and whatnot. And then 4 or 5 PhD students graduate from this topic, the topic that I'm presenting today. Okay, so I'll conclude my presentation here. And if you guys have any questions, and I'd like to answer.
Thank you, sir. Thank you for the wonderful speech, sir. Thank you so much. Questions? Any questions from the participants? Yes. You hear me?
Yes, I can hear you. Yeah, thank you for speaking Korean to me.
Okay. So just thank you for a very informative talk on AI/ML based closed loop control systems, intelligent stencil printing, and sensor printing in virtual environment. So that's very interesting for me. So just a couple of questions. So one, these ML models, what you prepare, I mean, are they common for all the assembly lines, or do they need to be trained or calibrated for each assembly line?
Okay, that's a good question. So technically, depending on the different setups, so we have to training individually, because if you receive the new job file, new component, even the equipment is the same thing coming from the same vendor, then there are some different specifications. So we have to train it separately. So I believe that this is another topic. So this will take a time. So we are trying to come up with a solution which can transfer the knowledge between the one line to the other. That's what we are working on it. But for now, individual training. Training for the individual lines. Sorry.
Okay, thank you. And related to the second question. So this to train the models for your research, are there any open data sets available, or are you getting it in some partnership with some company?
We have a lab, so we are creating all the data by ourselves. And so we have actually the sponsor, the companies, and they provide all these equipments and whatnot. So our students are doing the experiments and creating the data, and also the developing a solution, and then testing the solution with the existing line. So it's not coming from the open source data. And sorry to tell you, but we cannot also share, because there's a lot of the company like proprietary information in it.
Okay, thank you very much.
Thank you.